topic is conditional probability and Bayes' theorem. So basically, what is conditional probability is in conditional probability, we deal with two events, and what is specialty about these two events is one of these event has already occurred. So what is happening is we are now interested in two event probability in which one event has already occurred and the other event is yet to occur. That is what is called conditional probability. So in this case, today's topic, we are going to learn conditional probability and Bayes' theorem. Now this Bayes' theorem is nothing but another way to compute conditional probability in special cases. So Bayes' theorem also gives a way to compute conditional probability in special cases. Before that, we start with the usual definition of conditional probability. Let A and B be two events, then the conditional probability of event B, given that A has already occurred, is written as P of B by A is nothing but P of B intersection A upon P of A. So the conditional probability of event B, whichever this is the event which we are interested in, and the event A is the one that has occurred. This is already done. So we write it as P of B, the interested event, given that this line given that gets converted into the slash, and then it is A, and we write this as P of B intersection A upon P of A. Now although it is written as P of B intersection A, but it is always read as B and A. Similarly, P of A by B is defined. In this case, it is the event that we are interested in, and this is the event that has already occurred. So P of A by B is nothing but it will be P of A intersection B upon the down event which is there remains down. Now, in case if A and B are independent event, then P of B by A is nothing but it is P of B. That means what? The probability of event B, the interested one, is not getting affected by the probability of already occurred event. Similarly, P of A by B is same as P of A. That means in this case, the probability of interested event, that is event A, is not getting affected by the event which has already occurred, that is event B. Now we solve some simple problems on conditional probability. A dice roll find the probability that an even number is obtained given that a number more than 3 is obtained. First things first, when a die is rolled, we get the sample space as 1, 2, 3, 4, 5, 6. Now over here, if you read only the first sub question, it involves two events. If you observe carefully, find the probability that an even number is obtained is 1 and the other is number more than 3 is obtained. But one of these event has already occurred and it is clear which one it is. The event which appears after given date is the event which has already occurred. So we are now interested in probability of getting even number given that it is number more than 3. So this will be equal to probability of even number intersection. It is probability of even number intersection number more than 3 upon probability of number more than 3. Fine. So now, although it is intersection, this is read as and. So now when we are interested in this probability of even number and a number more than 3, we are interested in a number which satisfies both these properties. That is, it is an even number and at the same time it is a number more than 3. So 4 obeys the property and 6 obeys the property. So this is 2 out of 6. This is only for the numerator. For the denominator, we are interested in probability of number more than 3. So in this case, we are interested in the number 4, 5, 6. These are 3 numbers. Total number of outcomes are 6. So this numerator is the probability of this. Denominator is the probability of this. So now when we have two fractions on top of each other, we keep the first fraction as it is, write a multiply sign, and write the second fraction in a reverse order. We keep the first fraction as it is, multiply sign, second fraction in reverse order. When we cancel, we get the answer as 2 upon 3. Now we solve the next part of the problem. This gives us the answer for probability of even number given that it is a number more than 3. Fine. Then the next part, if you observe, is it is the same thing, that probability that it is an even number, but over here the second event, the event which is given that, or the event which has already occurred, has changed. So now it is a number less than 5. So in this case, what we do is we find probability of even number given that number less than 5. So in this case, it will be probability of even number intersection number less than 5. Although it is intersection, you can also write this as and upon probability of number less than 5. So what we do is even number and a number less than 5. So that means what? Now we are interested in those numbers which are even as well as they are less than 5. So interested number in this case is 2, this is even and it's less than 5, and 4. So these are the numbers in which we are interested. So we have got 2 which are favorable out of the total 6, and a number less than 5. And now we are interested in probability of a number less than 5. So now we are interested in a number less than 5. So when we are interested in a number less than 5, we are interested in 1, 2, 3, 4. So these are 4 numbers, and overall there are 6 numbers. So when we write this, since both these are fraction, top fraction survives, the bottom fraction becomes reciprocal, and you get 2 upon 4, which is 1 upon 2. This is how we solve a problem. Now we take another problem. A card is drawn from a pack of cards. Find the probability that the card is a face given that it is red card. So we answer this problem using this approach. So we are interested now in probability of getting face card given that it is red card. So this has to be equal to probability of face intersection red upon probability of red. Although it is intersection, we call it N. Now we are interested in those face cards which are also red cards. Now those face cards which are also red card. Now if you observe that there are 6 face cards which are also red card. Now these are what? These are the king which is of heart as well as of diamond. There is queen which is of heart as well as of diamond, and there is the jack which is of heart as well as the diamond. These are king of heart and diamond, queen of heart and diamond, jack of heart and diamond are total 6 cards, and these are out of 26. These are out of 52. So probability of getting a face as well as a red card is 6, because these are the 6 favorable outcomes and 52 are the total number of outcomes possible. And now we are interested in probability of red card. Now probability of red card, the favorable number of for a red card, the favorable number of outcomes are 26, total outcomes are 52. Remember over here we are finding the probabilities. We are not finding the number of red cards, which is why we have to write it as 26 upon 52. Even here, face and red card, we are finding the probability. We are not finding the number of face and red card, which is why we have to write it as a probability. So this will become 6 upon 52 upon 52 upon 26. This will get cancelled. We are left with 6 upon 26, which is 3 upon 13. Similarly, we do the second one, probability of king given that it is black. So this is equal to probability of king and black upon probability of black. Now among kings, there are only two kings which are black in color. So this answer we get it as 22 upon 52, and the down part we get it as 26 upon 52 for a simple reason that black cards are 26 in number. So these are the favorable cards. Total cards are 52. Over here, king and black are only 2 and total of 52. So we get the answer as 26 upon 52. Second fraction becomes reciprocal. You get the answer as 2 upon 26. And now again, the third part is given that it is spade. The third question is given that it's spade. It's spade. So now we are interested in probability of ace given that it is spade. This is nothing but probability of ace intersection spade upon probability of spade. You can also write this and as intersection as n. Now, probability of ace and spade is 1 upon 52 for a simple reason. There is only one card which is ace as well as a spade. There are 13 spades, but among those 13 spades, only one is an ace. So which is why 1 upon 52. And then we do probability of spade. There are total favorable outcomes upon 52. So this will come down to 1 upon 52 into 52 upon 13, and we get the answer as 1 upon 13. Now with this, we have come to the problems involving the definition of conditional probability. Now we do to go to another way to compute conditional probability in special events, in special cases. The Bayes theorem. Bayes theorem says if E1, E2, E3 up to En are n mutually exclusive and mutually exhaustive events associated with the same sample space S, and A is any other event associated with the same sample space, then probability of event EI given that A has occurred. This is read as probability of EI given that A has occurred. That means what? The has occurred part has come down. So there is a formula which says that this is equal to probability of EI into probability of A slash EI upon probability of E1 into probability of A by E1 plus probability of E2 into probability of A by E2. Continue this up to all the n events, which is given by probability of En into probability of A by event. The down part is nothing but the law of total probability. The down part is nothing but the law of total probability. Okay, so this is the formula in which we can get conditional probability of event EI given that E has already occurred, but this event's EI should be the n mutually exclusive and mutually exhaustive events. Only then you can apply the Bayes theorem. So we now see problems in which we apply Bayes' theorem. Of the students in a college, it is known that 60% reside in a hostel. So 60 upon 100. Now to convert this percentage into probability, we divide by 100. So it is given that this 60%, 0.60, 60 upon 100 is 0.60, is nothing but the probability of hostel. This is the probability of students living in a hostel. 40% are day scholars. Now what is day scholars? Day scholars are those people who go home and come back to college the next day. So this is nothing but this is the probability of day scholar. Then previous year results report that 30% of students who reside in a hostel attain A grade. Now if you observe that the 30% over here that is given, which is 0.30, 30 upon 100, is nothing but the probability of students who reside in a hostel plus they also get A grade. And the last, that is the 20%, is nothing but the probability of those students who are day scholars and A grade. Now, using the uh, given conditions and the question, our aim is to basically find the events E1, E2, E3, and A if all of these exist. Our aim is to find this E1, E2, and E3, and A if all of these exist. Now, event E1 is that event which has only one condition attached. So in short, your E1, E2, E3 are those events which have got only one condition attached, and there is a trick to check if the guessing of the events is done correctly. The thing is, the sum of the probabilities of all these events should be equal to 1. So in this case, if you observe this part, probability of hostel has got only one event attached. Day scholar also has one event. Over here, hostel and A grade has two things attached to it. And day grade, this school, day scholars and A grade, these are also two events. So your event E1 and E2 are those events which have got only one condition. So in this case, E1, we take it as hostel. Even E2, we take it as day scholars. And since there is no more single event, we say that there is no E3 for this problem. Now, we can again verify that this E1 and E2 are chosen correctly. What we have to do is, we have to just add this probability of E1 plus probability of E2. This is same as probability, since E1 is hostel, this is nothing but probability of hostel, and probability of hostel is given as 0.60, and probability of E2 is nothing but probability of day scholar, and it is nothing given but 0.40. So this will be 1. So our guessing, so our work of E1 and E2 is chosen correctly. Now, what we are left is to just choose the event E. Now this is pretty simple. Now among all these, the event which is left over is nothing but the event A. If you observe that hostel day scholar is used, what is only left is this hostel part is used, day scholar part is used, what is only left is this A grade. So therefore the event A is nothing but A grade. So now we are in a position to use the formula of Bayes' theorem. Basically, what we are asked, listen to the question. At the end of the year, one student is chosen at random from the college and he has A grade. So that means what? A student is chosen and it is found that he has A grade. So this event A, the event A has already occurred. This event A over here has already occurred for a simple reason. We are told that a student is chosen and it is he has an A grade. We are not told to find the probability that he has A grade. We are told that he has an A grade. That means the event of getting A grade, which is the event A, has already happened. Now, but we are told to find the probability that the student is a hostelier. That means we are now have to find the probability of event E1, given that A has already occurred. So, looking at this question, the question says find the probability at the end of the year one student is chosen from the college and he has A grade. It is told that he has, that means this event has already occurred, which is why this A is coming down, and we are told to find what is the probability that he is a hostelier. That means we want P of E1 slash A. Using the Bayes theorem, we get probability of E1 slash A using the Bayes theorem. See, the probability was given by probability of AI into probability of A slash AI. In this case, this I was a general term. Now we are interested in only E1, therefore we take the specific term. So this will be probability of E1 into probability of A by E1. So this is using the definition. The numerator in this case was probability of AI into probability of AI up slash AI. Since AI is general, we are now interested in only E1. We replace that I by 1. Now the denominator will be P of E1 into P of A by E1 plus P of E2 into P of A by E2. Now, although the formula over here has got n terms, we observe in our question that we could only get E1 and E2, and in majority cases we will only get E1 and E2. So therefore, we restrict ourselves only till here. Now we insert the thing, probability of E1 is given over here. E1 is hostel, E1 is hostel, and probability of hostel, if you observe, E1 is hostel and probability of hostel is 0.60. Now we want probability of A by event. If you observe, if you recollect, your event A is nothing but A grade, and event A1 is nothing but it is a hostel. Now if you observe in all these probabilities, A grade and hostel is this term which is involved. So therefore we insert 0.30 over here. Now we insert probability of E1 is 0.60. Probability of A by E1 is 0.30. This probability of E2, if you observe, is E2 is day scholar, then probability of day scholar is 0.40. So 0.40 into probability of A by E2, that is A grade, given that is hostel, so it is nothing but it is this 0.20 that we get. So when we multiply, we get it as 0.18 upon 0.18 plus 0.08. So this is 0.18 upon 0.26, some value you will get. So this is the probability. We now move to the next problem. In answering a question to an MCQ, a student either knows the answer or guesses the answer. 3 by 4 with the probability that he knows the answer, 1 by 4 with the probability that he guesses the answer. Assuming that a student who guesses at the answer will be correct with a probability 1 by 4, what is the probability that a student knows the answer given that he has answered correctly? So in this case, we write down first all probabilities which are given to you. Observe that the first number or first probability that is given to you is 3 by 4. Now 3 by 4 is the probability that he knows the answer. So probability that he knows the answer. 1 by 4 is the probability that he guesses. It's clearly mentioned over there. Okay. Assuming that a student who knows the answer, who guesses at the answer, So this 1 by 4, the other 1 by 4 which is over here is nothing but a student guesses at the answer. He guesses at the answer along with correct. He will be correct. So this is nothing but probability of guesses plus correct. So using this, it is very easy to define what our E1, E2 and E3 will be. E1 in this case will be those events, or E1, E2, E3 will be those events which have got only one condition attached. Now clearly looking at all these things, E1 is nothing but this knows the answer. E2 is nothing but he guesses the answer. Now there is no E3 because these are only the two events which are only one condition attached. So there is no E3. Now A is that event which is left over. The event which is left over is the getting correct. Now we have to know what probability we are told to find. We are asked what is the probability that a student knows the answer. We have to find the probability that a student knows the answer given that he has answered correctly. Now if you observe that given that he has answered correctly is this is the event A. This is the event A. He has answered correctly is the event A, and the student knows the answer is nothing but this is the event E1. So we want probability of event E1 given that we replace it by stroke, he has answered correctly, that is we replace it by A. So using the Bayes' theorem, we get probability of E1 slash A is nothing but probability of E1 into probability of A given that E1 has occurred upon probability of E1 into P of A by E1 plus probability of E2 into P of A by E2. Now probability of E1 over here, E1 is nothing but knows the answer, and probability that he knows the answer is 3 by 4. So 3 by 4 is nothing but, if you write it in decimal, it is 0.75. So this is 0.75 into, we are asked what probability of A by E1. Now we want what probability of A by E1. Now A is what he knows the answer, and E1 is that he no A is not the answer. A is the answer is correct, and E1 is he knows the answer. Knows the answer. So if you observe that over here, there is nothing, no probability mentioned in which the answer is correct as well as knows is given. So there is, for P of A by E1, the value for us is not given. P of A by E1 is what A is, if you observe here, the answer is correct, whereas E1 is knows the answer. So when we write A by E1, it is correct and knows the answer. So this value is not yet given. P of E1 is 0.75 into, we leave this blank because P of A by is not given. P of E2 is given to us as E2 is gaseous, and probability of gaseous is 1 upon 4, which is 0.25. You can check it using calculator. 0.25 into probability of A by E2. Now this A is nothing but correct, and E2 is a gaseous. So correct and gaseous is given over here, and this is actually 1 by 4, which is 0.25. Now probability of A by E1 is what? It is basically correct and knows the answer. Now we now find this value of probability of A by E1. Now So now this probability of A by E1 is nothing but it is probability that his answer is correct given that he knows the answer. So the value of this probability is always 1 for a simple reason is when you know an answer, it is 100% sure that you are going to answer it correctly. So that is why the probability of getting an answer correct, given that you know the answer is always 1. So probability that you answer correctly, given that you know the answer is always 1. So therefore, a P of A by E1 is 1 and P of A by E1 is also 1 and we get the answer as 0.75 upon 0.75 plus 0.0625. We get the answer as this 0.25 into 0.25 is 0.0625 and this is actually 0.75 upon 0.8125 and this you will get the answer using calculator. When you add this you will get 0.8125. So we now come to the end of this conditional probability and Bayes' theorem part. Basically, conditional probability definition has to be used only in case of finding conditional probability of simple events. Like in this case, these are all simple events. A die is rolled, a card is drawn. But when you have some complex event and when you can get this E1, E2 such that the sum of their probabilities is 1, it is then you have to use this Bayes' theorem, which also gives another way to find conditional probability.